I am ready.
Just tell me when things are...
You are good to go.
Okay. So, hi everyone. I'm very happy to introduce today's seminar speaker, Katherine Turner. Katherine comes from us today from somewhere between GFDL and University of Arizona, which, if you average that, is Arkansas, right? No, not quite. She's got a split postdoc position between GFDL, where she actually resides, Geophysical Fluid Dynamics in Princeton, and University of Arizona, working with Joelle and Russell at Arizona, and John Crasting, a colleague of mine, which is how we met at GFDL. So, a bit of her background: she's got a Bachelor's of Science in Pure Math from Texas A&M. Go Aggies, go Aggies, yeah, something like that. And then she crossed the pond for her graduate work. So, she did a Master of Physics at Guiomar, working with Rick Williams and Andres Alschluz. Sorry, I'm misreading your CV. Sorry, and a PhD working with Rick Williams at University of Liverpool. Working on topics such as transient climate sensitivity and carbon uptake, which are also taught. And then you did a postdoc afterwards at University of Liverpool, continuing on such topics. And then she came back over the pond to work as a postdoc with GFDL and University of Arizona. She's got a very cool CV of all sorts of fun topics in the areas of Southern Ocean, connecting, timescales from weather to ocean climate timescales. And I think my favorite thing in your CV, which folks in this department will especially appreciate, is you've worked with students on connecting climate change to music and how you do music composition, which we're going to have fun talking about later, since that's an interest of mine. And there's also a bunch of other musicians sitting in the front row. So today's topic is on the Southern Ocean, how it responds to storms, so on that time scale interaction piece. And take it away, Katherine. Thanks for coming to visit.
All right, thank you, Liz. Can everyone hear me okay in the back? Awesome. All right, so this is really exciting for me because this is the first really academic talk I'm going to give on this work, which I've been doing for the last 9 months as part of a SOCOM postdoctoral position. And SOCOM stands for the Southern Ocean Carbon and Climate Observations and Modeling Program. So this massive program where we are really trying to use as many new sorts of observations as possible to understand how the Southern Ocean works and relates to our global climate. Liz covered most of this, but here's another, just another little slide about me. I'm back in the U.S., my home country, so this is really great to start getting involved with the American climate science community, so thank you so much for having me. My main interests involve the climate response to emissions, large-scale ocean heat and carbon uptake, and ocean ventilation. Outside, I get incredibly seasick, so most of my activities remain on land. So when I think about my main motivation for being a climate scientist is this figure right here. This is the transient climate response to emissions, which is a near path-independent and linear relationship between cumulative carbon emissions here and average surface warming. And it's this relationship that allows scientists and politicians to try to constrain for allowable ranges for emissions that are consistent with what we consider to be sufficient levels of global warming. When I think about this transient climate response, to me, it is ultimately an ocean thermocline ventilation response, because the amount of warming that we get per unit emissions relates to both how the Earth system takes up heat and carbon dioxide at the same time. And luckily, the ocean has has a strong compensatory response between its carbon uptake and heat uptake on multi-decadal to centennial timescales, thanks in large part to the fact that most of this uptake is occurring along the thermocline. And so because I'm interested in this ocean response, it's very natural to start thinking about the Southern Ocean response. The Southern Ocean is really interesting to me because it is a relatively small ocean basin, but still takes up a massive amount of anthropogenic heat and carbon. And a large part of this is because it's very wind-driven. So in this zonal average plot of Southern Ocean overturning, we get eastward winds or westerly winds for the meteorologists in the room that bring up very old, cold, and natural carbon-rich waters. And then these waters are allowed to re-communicate with the atmosphere after multiple centuries of being isolated from it. And then for thermocline ventilation, these winds also drive a northward Ekman transport, which turns into subduction into the main thermocline. So, but then when we think about the winds, what are we actually thinking about? We have westerlies in the Southern Ocean, but if you were to ever look at a synoptic map of surface winds, you might be hard-pressed to actually see them. And that is because the Southern Ocean is the stormiest ocean region in the world. And so it's consistently battered by these synoptic low-scale systems that travel along the winds. And these storms in the mid-latitudes impose super strong winds. They induce very large waves, and they also create enormous air-sea fluxes, and they also impact the relationship with radiative forcing due to anomalies in our cloud cover. So one question that I am trying to look at as part of my postdoc is how do we best understand the role of these synoptic scale features in setting long-term climate scale behavior? So my main takeaway is that I'm going to be using climate models to try to understand the storm tracks in the southern hemisphere and their impact on climatological southern ocean ventilation, and then move on to heat carbon uptake. So in my talk today, I'll present some initial storm statistics from the GFDL models that I have been working with. I will present some results of storm-centered composites of atmosphere and ocean conditions that occur during a storm. Some impulse response work that we've been looking at for mixed layer depth anomalies after a storm has passed. And then also a bit of an introduction to other work and future avenues that I would like to pursue throughout my postdoc. So first off is the question of how we actually track storms. So I feel very blessed to be at GFDL, where we've got a whole slew of climate model output that we can start working with, and so I live in model world. I'm able to use a feature tracker using a piece of code called tempistic streams to isolate low pressure systems that are consistent with these synoptic scale storms, and it isolates them and then tracks them throughout time. And so you can get a spaghetti plot like this where you start to see the storm tracking. The storms are consistently moving both eastward and poleward. And so the models that I'm using are, it's sort of a hierarchy of the coupled model that GFDL has, where we've got setups where we can increase the atmospheric resolution from 1 degree to ½ degree, and then we've got another setup where we increase the ocean resolution from 1/4 of a degree to 1/8 of a degree. So we can really start to look at what the impact of horizontal resolution is. And then because in model world, this means that we can end up getting a large number of storms that we can create some really robust statistics from. And so for each of these models, if you integrate it for 100 years, what that ends up meaning is you'll get something on the order of 10,000 storms in the Southern Ocean over a century. And then from those 10,000 storms, if you take snapshots of the atmospheric conditions or the ocean conditions, you'll end up getting about 100,000 snapshots of those. So what do the storm tracks in my model look like? So these are storm density plots for 100 years in each of the runs. So this is the normal coupled model here, and then we increase the atmospheric resolution as we move here, and then the ocean resolution as well as we move over to the right. And the storm track can be seen through the brightest colors. So this is where you have your highest density of your storms. And so for all three of the models, you see that the storm track becomes its densest as it reaches like the Indian and the Western Pacific sectors, and that's consistent across all three models. But you do start to see some differences in the models with different horizontal resolutions. So if you take the difference from these density plots, you get these plots down here. So this is the number of storms in the higher higher resolution atmosphere minus our normal model, and then the same comparing this model with the higher atmosphere and ocean resolution to our original model. And so what we can see here is that you have increased storm activity everywhere when you start to increase your horizontal resolution, but you get you get a few hot spots. Ignore this one, but that's a coding error. But the other ones are real. So like particularly in the western part of all of your basins. So when you increase your atmospheric resolution, we're getting this hot spot in the western sector, or in the western part of our Pacific sector. But then when we increase both the atmosphere and the ocean resolution, you're getting the same hot spot here. This becomes a little bit, this starts to shift around a little bit, but then you start to get hot spots also in the western part of your Atlantic sector, and then you can also start seeing something pop up a bit more in the Indian sector as well. But of course, with this being model world, it's not exactly real, and so just as a bit of a humility slide, I've got a comparison to storms that we actually get from some of our reanalysis products. So this is comparing the storm density to the storm density found in Era 5, using the years 1979 to present to try to account for the satellite era. And so what we can see is that the biases have a very strange spiraling pattern where you get more storms in the models in the western part of the Atlantic, and then it kind of spirals in towards the continent. And then you've also got this area of increased storm activity in the models relative to the reanalyses. And then you've got kind of, you've got this striping as well, where the models are producing fewer storms south of Australia, and that has a similar sort of striping pattern. And then as well, you see a similar sort of signal in off of South Africa. Why this is the case, we don't know, but it is something to keep in mind because these are the runs I'm looking at are fully coupled. So even though the statistics may not be exactly the same, hopefully the dynamics are self-consistent, and then we can try to think about this problem once we better understand what's actually going on in the models.
Can I?
Yeah.
Sorry, can I just ask, because you're here comparing the pre-industrial control runs to the historical Era 5 data, is there a possibility that there's a forced signal in there?
Yeah, oh definitely. I mean, it would have, so this is going to be a combination of two, of multiple things going on. Parsing them apart is going to be difficult, but I also want to do some work with more historical and future scenarios. So maybe in the future I can explain this a bit better. Any other questions up to now? Okay. If not, feel free to raise your hand or interrupt. Oh, go for it.
A quick question. So have you also looked at whether the intensity of the storm compares between the reanalysis and the model, or?
Yeah, so that's an interesting question because defining the intensity is not necessarily straightforward, at least to me. I'm not a meteorologist, so somebody might be able to answer this one better. But yeah, it's, I'm currently working on another project that is using actual data, Era 5 data, but then also ocean only model runs driven by those data. And so my colleague would probably know a bit more, but I cannot answer that right now. Okay, so moving onwards, I have a few composite figures of what a storm looks like in the Southern Ocean. And this is more of just a check to see if the model is kind of doing what we expect it to do. So this is taking every storm tracked in the models, taking a picture of whatever fields you want it to. So here I've got sea level pressure, and I also have wind speeds, and then you can create an average. And so these are the averages of the 100,000 storms that I was talking about earlier. So a good sanity check is that a storm is associated with a sea level pressure minimum, which is great because that's what we want. And then the wind speeds are also consistent with what we know about storms. So we've got the right direction of rotation in the southern hemisphere, which is great and not always something that you can rely on, apparently. Anyways, and then you can also see that the winds reach their highest maximum, or reach their highest values just north of the storm center. On the ocean side, we can start to look at the anomalies for fluxes. And so this is now looking at the communication between the atmosphere and the ocean when a storm is passing. So I've got over here on the left carbon flux anomalies. Don't worry too much about these units, but so two things to mention is that red is outgassing of carbon dioxide, and that these composites are taken in degrees away from a storm center. So when we think about a storm, like the storms are like a few thousand kilometers from one end to another, and so this is looking at a radius of 10 degrees away from the storm center. So when we're talking about like short-term ocean responses, this is actually very large scale, because normally when we think about small time scales, that kind of coincides with small length scales as well when we start looking at our mesoscale and sub-mesoscale variability. This is actually really large scale. And so what we have here is a large area of carbon outgassing to the north of the storm, which lines up actually pretty well with our wind speeds, implying that this could be mainly a piston velocity sort of response. But then you do see a smaller area to the perimeter where you get some level of carbon dioxide uptake. For our heat flux anomalies, the colors are now the blue, which is a heat release from the ocean to the atmosphere, and then the red is a heat uptake into the ocean from the atmosphere. And so we've got a large region where the ocean is releasing heat from into the atmosphere, and then a smaller region where that heat is going back into the ocean. And the interesting thing to know about this, which I did not know, is that the zero contour is consistent with an occluded front. So you can really start to see the frontal structure of these storms when we start looking at these anomalies in a large statistical sense. Yes?
Katherine, I've always wanted to ask this question. This seems an appropriate time to do so. This is an area that you're looking at for both anomalies of fluxes, right?
Yes.
Does the model take into account the corrugation of the ocean surface that is a function directly of the winds? So in other words, this is not a square, this is not a circular area. It's a lot more area than pi r squared. And does that get taken into account? Because that seems to be a really primary effect of the storms, to corrugate the surface.
Yeah, so I don't know if there are, maybe someone can answer this better, but I don't know if there are global climate models that actually have a free surface that evolves with surface waves, because they don't represent the surface waves.
Yeah.
The coupling time step is too long for that, but I also don't know if they're moving towards that. So if I were to take a guess, I would say this is a flat ocean that we're looking at here.
Because I've always wanted to know, what is the increase in actual area exposed from water to air when you take into account the corrugation of 60-foot waves in that region of high winds?
Right.
It's probably not small.
No.
The ratio is probably large.
Yeah.
So anyway, thank you.
Yeah, that's really interesting. No, I hadn't thought about that before. Yeah, this is a global model, so there are a lot of assumptions that are made in these super small scale processes, and I would have to ask to see how those are being represented.
Thanks.
And then what I'm really interested in is starting to understand the upper ocean response to these storms. And so right now I'm a bit data poor, because normally in a global climate model, most of your ocean fields are being spit out at either a monthly resolution or an annual resolution, which is mainly like a function of how much space you have on your machines to store like multiple, what's now starting to get up to like petabytes of carbon data or climate model data. But what I have right now are daily mixed layer depth anomalies. So we can do the exact same thing, but now starting to look at how the mixed layer is responding to a storm. And what we get is a really nice dipole structure, which is different to the other dipole structures that we have for our heat or carbon flux anomalies, and now has So these mixed layer depth anomalies indicate a deepening of the mixed layer. So the positive anomalies are when the mixed layer goes down in blue, and that is found to be north of the storm center. And then you have a mixed layer shoaling, or the mixed layer being brought up directly underneath the storm, but then also broadly to the east and the south of the storm. When I first showed this to my group, they all joked that it was the Pepsi logo, and that's what I had come up with. So yeah, this is a really interesting, like, large-scale feature to these storms, and these anomalies are, you know, plus minus 8 meters. So it's not completely, like, insubstantial. Like, compared to the seasonal cycle, it is small, but the mixed layer is constantly being battered by storms at this point. So it was really interesting to see this sort of response. But one of the caveats with looking at these sorts of composites is that you're following the storm as it's going all around the ocean. So you're getting the storm in all stages of its lifespan. But then as well, you're never actually seeing what the ocean is doing after the storm's passed, which, when we start thinking about, like, the impact on a climatological scale, we really need to start understanding what the ocean is doing afterwards. So for the mixed layer depth, what we've done is we've created static masks to really take snapshots of what the ocean is doing for a period of time after a storm has passed. And just to give you an indication of, like, how stormy the Southern Ocean is, you're gonna, like, if you're just like a region in the ocean, you're gonna get impacted by a storm approximately every, like, 3 to 5 days. So these snapshots kind of start to show the persistence of these mixed layer depth anomalies. And what's really interesting is that we were thinking that by day 3 or day 4, we would start to go back to kind of our climatological state, so we would have no more anomalies in our mixed layer depth. If we had, like, a purely stochastic forcing that didn't have any persistence, that's kind of what we would expect. But what we're finding is this dipole structure is actually existing for like 2 weeks almost. These are just the first 9 days. And obviously it does get damped, but the fact that it's still there is pretty amazing in my opinion. One thing to note is that I've been trying to calculate damping timescales for the different parts of the mixed layer response, and the deeper mixed layer is more persistent than the shallower mixed layer. I don't know if you can see it based off of the color bar in the projection, but the E-folding timescale for the deeper mixed layers is like 4 to 6 days, whereas for the shoaled mixed layers, it's closer to 1 to 4 days. So this is as far as I've got with my analysis right now. Oh, no, that's not true. I've also been trying to tie this back to the differences in the storm density that we were seeing before when we were just trying to track these storms using the atmospheric fields. So I've constrained my composites to only really consider storms that are in this part of the western Pacific sector, which is where we had that first hotspot that popped up when we increased our atmospheric resolution, but then remained when we increased our ocean resolution. And so this plot is showing the difference in these composites between this, the model with the increased atmospheric resolution, and then the original model, which was this one. So things to note is that these anomalies range from like plus minus 10 meters. When we start looking at the impact or the difference between these two models, the changes in the mixed layer depth are now more like plus or minus 5 meters on t equals 0. I need to look at these figures some more. This is like the newest stuff that I've done. But what pops up in my eye is that we see an impact we see a difference in the two models that kind of has another sort of dipole structure at t equals 0, which is right when the storm is over the ocean. As the as the storm leaves, the situation gets a lot fuzzier. These look quite noisy, and there's some noise that is due to the numerical aliasing, which I won't get into, but that's not physical. But it does, like, the rest of the noise is the actual model differences. And then very weirdly, after about a week, we start to get another sort of like positive area here. So a shoal, like a more shoaling in the model with higher atmospheric resolution. So I really don't understand this. I don't know if I should believe it. But this could be partially because of the increased storm activity and the changes in how often the storm is battering the ocean. But it could actually be something else inherent in the coupling for the model. What's more interesting is actually when we start to look at the impact of the ocean horizontal resolution. I said circulation, but I don't actually know if that's the case. So now this is comparing the two models with the high resolution atmosphere, but one of the models has an 1/8 of a degree ocean resolution. So this is really trying to isolate what the role is of having more small scale processes be resolved in your ocean, and how that impacts the persistence of these mixed layer depth anomalies and the structure of them, really. So first thing to note is that the differences here are actually larger than the ones between the two atmospheric model setups. So we're now getting, again, plus or minus 8 meters in our initial anomaly. So when we've got a higher resolution ocean, what we get is more deepening of the mixed layer in the south, and then more shoaling in the north, which is, so it's compensating for the overall impact of the storm on the ocean. Yeah, so because it's the opposite sign, this dipole here. You can see that this signal propagates east as time passes and the storm passes. So this could potentially be just a signal of the storm center also moving a certain number of degrees, but then it does dampen out after about 4 days to the point where we end up getting some noise, but potentially also, yeah, whether it's noise or structure is something that I'm still working on. But then the nice thing of it is that we can start to compare, we can compare those two maps or two plots to each other to start to parse whether the ocean or the atmosphere resolution is playing a larger role in our mixed layer depth anomalies associated with these storms. And so this is just the sum of the two plots before, and my main takeaways so far are that we are getting this southern signal, which is mainly coming from the increase in our ocean resolution, whereas we're getting a bit, and then for the northern part, north of the storm, we're getting this smaller signal that is mainly kind of like popping up and staying consistent about like after a week. And that seems to be more related to the atmospheric resolution. So in terms of my research, like this is really as far as I've gotten. So at this point, I've got a lot of questions about like how to try to parse these impacts and try to understand them. So yeah, just to recap, these are the findings that I've got so far throughout my postdoc. The first one is that storm density and location in the southern hemisphere are both specific to the model that you're looking at, or whether you're looking at reanalyses, and that it is sensitive to the model horizontal resolution. We are finding that there are unique and robust patterns of the anomalies that we are seeing that are associated with these storms for both atmosphere and ocean fluxes. and then also some upper ocean properties. And then we're finding a long-term, which I put in quotations because I'm talking about the order of days, and so anybody working on like seasonal timescales is already long-term to me. But there does seem to be like a relatively long-term persistence of these mixed layer depth anomalies associated with the storms, which gives us quite a bit of optimism that we might actually be able to characterize the overall impact of storms on longer timescales, and that is not just a stochastic sort of random response, but with a big caveat, that being that the structure of this persistence and its evolution over time also seems to be quite sensitive to how we are resolving processes in our models. That's my project. I just want to introduce a few other things that I'm working on or helping with as far as the postdoc goes. So obviously I've been working mainly with model data, which I love doing, but at the end of the day, what we're really interested in is understanding how the Southern Ocean works here, like on Earth. And so we are trying to also understand what current observations are telling us. So I've got a colleague, Magdalena Carranza, who's at Mbari, and she's actually been doing this really great work in looking at the mixed layer depth anomalies and the carbonate system using these biogeochemical Argo floats. And so you can do the same sort of compositing where you take the measurements from these biogeochemical Argo floats and you can plot them relative to where your storms are located. And then you can also start to understand some of the persistence. And the really interesting thing that she's found is that we do get the same sort of persistence in our mixed layer depth anomalies over time, so they are lasting for multiple days, although they are less persistent than the ones in the model. But then when we look at the mixed layer depth anomalies just by themselves, it's a large scale deepening of the mixed layer depth. So we're not seeing this dipole structure at all when it comes to looking at the observation. So that's really interesting, something that has not really been answered yet, and we've got a few ideas, but at this point it's still pretty speculative. And then kind of touching on what you mentioned earlier in terms of the storm track, I'm also interested in trying to take what I can learn from a climatological sense for the Southern Ocean and see how it applies to our future climate. So when we think about the southern hemisphere winds in a warming climate, they are projected to increase and move poleward. And so I've been starting to look at a few different scenarios and doing the same sort of analyses for the storm tracks themselves. So these are the pre-industrial control runs that I've mainly been working with, but then I've done it as well for a 30-year historical period from 1985, and then also the last 30 years of the high emissions SSP 5.585. And so when we take the difference between these scenarios, we are seeing a poleward shift of the storm track that can be seen in this area of blue where we have fewer storms and then the nearby area of red. But also, it does seem to be that there are just, at least in the model world, there are just fewer storms in both the historical period and the end of SSP 585. So this is really interesting to me because it changes the balance of what our storms look like in terms of being more of like a laminar, like westerly flow versus this very highly eddying synoptic scale feature. And then also the difference in location is almost certainly going to alter some of the relationships between storms and the underlying ocean, because we will shift where these storms are relative to sea ice, where moon water formation is happening, the pattern of upper ocean stratification, but also then changes in that as we get into a warmer world, and then also the major current systems in the Antarctic. I've got a lot of future work to do. This is really the beginning, so it's really exciting for me just to get to explore. But what I ultimately want to do is start to rerun some of these models and create budgets for the response to storms. So this is going to be taking output on like daily timescales for like the entire upper or the entire Southern Ocean, and trying to understand what exactly are the physical processes that are determining the ocean response, both in terms of its structure and its persistence. And then looking at other models and trying to understand a bit more about the actual couple dynamics of the models to understand what exactly is going on with this horizontal resolution. And then ultimately, like, my dream would be if we could somehow get a number to the total storm force, like heat flux or carbon flux or ventilation rates, even in terms of like a pre-industrial sense. I think that would be really fascinating and amazing. So that's kind of my pipe dream for this job. And so I've got here my take-home messages. I really appreciate being able to talk to you guys about this today. And I guess I would just like to end with like an advertisement. Like, I'm new in this field where weather and climate start to merge, but I think it's fascinating. And so if anybody else is also interested in that, my email's down here. Maybe we could chat. So with that, I'll just open the floor to questions. Thank you.
Cool. Let's start with this student question from Steph.
You mentioned that in the Argo criteria you weren't seeing that dipole that you were seeing in the model data, and I was wondering what were some of the hypotheses that your team was having for that sort of difference?
Yeah, so the main hypothesis that I'm working on right now is that this is a difference in terms of how many observations we have. So with the model data, the fact that we're able to have like tens of thousands and hundreds of thousands of like outputs to try to create these statistics has been really powerful, because the response to storms can vary massively. Like, especially when you start thinking about anomalies, right? Like, you're taking your anomaly relative to some climatological value, but that anomaly includes all of the anomaly associated with some interannual variability, the anomaly associated with like more decadal timescale variability, perhaps in like where your storm track is due to like larger zonal wave numbers and stuff. So we do in the model have a lot of mixed layer depth anomalies underneath storms that look like this as well. So I'm hopeful that they're not so inconsistent that the model output is just useless. I'm really hopeful about that. But yeah, it's something that we have to explore more. Also, like, Argo data is super new, right? Like, we've really been releasing them for like the past 20 years, I think, in total, but like in earnest, it's really been like the last 10 years, particularly with the SOCOM project that's just released a ton of these. So yeah, we need more observations, really. I would love to see that too. So I think there's like two sides of the problem. Yes.
You showed looking at the time after a storm passed. Did you consider what part of the life cycle the storm was in? Because it looks like the frontal structure is really important from your earlier plots.
Yeah.
And I wonder if like a passing included cyclone is going to be a different impact than passing early cyclone.
Yeah, so something that I should have mentioned before is that when I created these static masks, just so that my computer, it was mainly like a computational time sort of thing, but I took the mask to be static where a storm reached its lowest sea level pressure in the center. So these are supposed to be like the mature storms that I'm using for t equals 0. But yeah, you can do the same thing with storms in different life stages. I think there are a lot of ways that you can break up storms as well, in terms of like where they're being generated, where exactly what part of the ocean they're going over. And so there's a lot. There were like also in their occluded phase when they start to fizzle out. So this is kind of like a simple but yes arbitrary choice in terms of how I am quantifying this persistence after a storm's passed.
Do you think your results are like applicable outside of the Southern Ocean?
I mean, I think the Southern Ocean is really special when it comes to this because you don't have any land masses blocking your storms. So storms in the Southern Hemisphere behave really differently to storms in the Northern Hemisphere. Like if you look at the storm track, the Northern Hemisphere is the storm track is really set up by these zonal wave numbers that are determined by the setup of land masses, right? So your Himalayas, your Rocky Mountains. Whereas in the Southern Ocean, we're really lucky in that we only have land like here, pretty much. And so your zonal wave numbers are either, I don't know if it's, you either like don't have one and it's just like purely circular, or you have zonal wave number 3, which is like a little triangle under sea level for sure. So I think in terms of like overall, I don't know enough to say like this is definitely applicable to like the North Atlantic or something. But if I were to guess, I would say that the frontal structure would probably be quite consistent with like other storms. I mean, with the caveat of flipping everything because of the rotation. But yeah, I've not actually looked elsewhere, but that could also be very cool.
Cool talk. There's a lot of interesting stuff here. One thing that I'm thinking about in thinking about how to bring like sea ice into some of this conversation, I think it would be really interesting to do some of these composites based on how far away you are from the ice edge, because I feel like if you're looking at an oceanic response to atmospheric forcing, but only part of the ocean feels what the atmosphere is doing, that might be part of the reason that you see stronger anomalies to the north of your systems in a lot of your plots here and here, because in some of the storms, maybe only half of the storm is even communicating, and then that'll also change your, like, where your divergence is happening from Ekman transport and that sort of thing. So, like, or even seasonality, like, you have storms in the same place, but for part of the year, the sea ice is going to be up against it, and for part of the year, the sea ice is going to be, 1,000 kilometers away. So, I think that sort of analysis would be really cool as an addition to this.
Yeah, I am currently working on that as well, because it's a really good point. The sea ice is really effective at serving as a barrier between the atmosphere and the ocean. And it will have major implications for how storms impact the Southern Ocean as we change our sea ice coverage in the future. So yeah, I've not done that just yet. But yes, it's definitely something on the to-do list that I'm currently working on.
John.
I think to the prior question, not Evan's, I don't know if it was Jerry's question, I couldn't tell who it was, about what's applicable to the northern oceans, northern hemisphere. I think there are differences in the storms. I think that, and you hit on one of the reasons, it strikes me that a more zonal flow in the southern hemisphere means that cyclone development relies more on shear vorticity advection being moved around than curvature. And the consequence is different structures to the storm. I think, this is all a hypothesis, but I believe there's some reason to believe it. And so that the method you're using, absolutely, you can throw it in any part of the ocean on the globe, and it's really great methods, fantastic work. But I bet you'd find some intriguing differences. And I think those differences could be traced back to the nature of developments at sea level between the hemispheres. I don't think they're the same.
Yeah.
They operate with the same rules, of course, but the environment is different, and so the available ingredients for development are different systematically.
Yeah.
And it's interesting.
That is interesting to think about. Yeah, I really don't have a lot of meteorological background, so I know nothing about like how storms form outside of like these very idealized like model sorts of frameworks.
Well, I'm glad you gave your email address. I'll be happy to.
Yeah, I'll put that back up in case you want to write it down.
Is this
about how you go from your individual storm perspective to kind of like what's the climatological impact of this. I'm more familiar with terrestrial work on this, but there's been a few papers on that side where you can show that, for example, the year-to-year variability in terrestrial carbon uptake in any one location is really kind of controlled by a handful of really nice days in the summer, right? Favorable weather conditions, like it's really like 2 of those versus 6 of those. That is going to be a larger driver of kind of the net carbon uptake. I don't know if there's an analogy here for storm frequency or number, and like, if that pattern that you have on the carbon side, I think they do the same for the heat side, is the same, right? Then is there some way to say like this is X percentage of the net carbon budget, increasing or decreasing every year? I don't know, I'm just curious what your thoughts are.
Yeah, so there have been some papers that have tried to quantify the impact of like the most extreme wind events on carbon outgassing in the Southern Ocean. I think we can do one better because the benefit that we have with ocean and like ocean carbon, ocean heat is that we can get interior inventories, right? And so that is really where we're going to start seeing the integrated response, right? Like a flux, particularly in the Southern Ocean, it has a massive seasonal cycle that we absolutely need to try to understand. And then storms are even like smaller scale relative to that. So in terms of like just understanding the fluxes, I think that's a really big problem. I'm really hopeful that once I start getting these higher frequency outputs for the interior as well, we can start to put it in a way where we can be more confident about the longer time scale impact of these very synoptic events.
Yeah, thank you. Great talk. I think you're in a really fortunate position there because you have all this incredible data to work with, right? What I wanted to get back to is that you mentioned the wave number 3, the zonal wave number 3, and I don't really see it in your like
in my spaghetti plot.
Well, not in your spaghetti, but also in these ones. More like if you go back to here, kind of see a hint, like the Amundsen sea low, but it's not very pronounced. Have you compared it to observational composites of this? I don't know whether you showed one.
Yeah, I think the benefit, so zonal wave number 3 kind of gets smeared out just because these are 100 years of sea level pressure that we're analyzing. I've not done, I think what would be really interesting would be to look at different periods of the historical record with like era 5 or something, see the periods that we've got a strong zonal wave number, and then start to isolate our analyses for those. Because I also don't know a lot about zonal wave numbers, as if I'm not even entirely sure if there's sea level, if that's based off of sea level pressure or something more aloft. That would have to be something that
it shows up in both. 500 and sea level pressure.
And so, part of the reason why I'm asking is because you have a signal, when you compare those, right? You have a signal where the Amundsen sea low is deepening. You showed that in the later ones.
And like here.
Further, close to the peninsula there. You compared the runs later, and so I was just wondering because, like, from what Evan was also mentioning about sea ice, it's always that discussion that the evolution of that wave number 3 pattern is responsible for how the sea ice changes. And so I would just be interested, like, if you compare those to the observational equivalent, whether you get the same spatial pattern. Because I also, I would really be interested in, like, do you have any like physical intuition for why you get the dipole in the mixed layer depth?
So to first order, this is consistent with the Ekman transport from wind stress curl. So we've got our strongest winds blowing this way, just north of it, and so that is going to induce anomalous northward transport, which would transfer water in the mixed layer from here to here. The exact details, still open for some work. But that's kind of how I've been trying to understand it first, but without looking into it more deeply.
Yeah, very cool.
I'll ask the last question. Oh, do we have, was there one in the back?
Do you have a? Oh, okay.
Okay, so you show that nice schematic by John Lauderdale at the beginning that has upwelling and, you know, DIC going in here, out there, CO2 going in there, Ekman transport. How does, you know, thinking on this storm-centered perspective change this, you know, schematic? I mean, you're showing basically outgassing and ingassing, whatever the right word for that is, you know, based on where the storm is.
Yeah.
So would you modify this to take into account what's actually going on at, you know, human time, or like timescales of the actual storms that are probably doing, I would guess, a good chunk of the work that this schematic, you know, averages over?
Can I answer that in like a year? Sure. Yeah, I think I mean, this is obviously very climatological. Like, this is also not how upwelling works. So I don't think I would change this figure. I think I would create a separate figure for maybe the upper ocean response to a storm, because I mean, it's correct. Like, we need to take the mean of these winds. They are generally an eastward wind, and so that like the whole Ekman, the overall dominance of this Ekman transport is, I think it's correct. I'm not looking to ruffle any feathers or shift any paradigms here. Just trying to understand a little bit better. But yeah, I would need to think about that a lot more.
Any last questions?
Well, can I just follow up on that?
Sure.
There are individual actors that contribute to this,
Mhm.
and that's what you're looking for.
Yeah.
And I think that's cool.
That positive note. Let's thank Kathrine again. If anyone is super intrigued by this, there is still a gap or two in her schedule, and she'll be here all day, so just, you know, let one of us know. We'll have a nice lunch.